Hello, this is Lec2-stat135. Today, announcement, homework 1 is now available on B courses. And what we covered last time, we were looking at a dichotomous case where your box is 0, 1, and you have a sample size n, sampling without replacement. So x1 to xn are Bernoulli P, and the sample mean is given here. The expectation of the sample mean is the expectation of x. Actually, we'll show that a little bit later, but perhaps that's obvious. And the expectation of x is p, is a property of Bernoulli. The variance of x bar we showed is given the formula here with the correction factor at the end. Today we're going to attach ourselves to the book, section 7.3.3, the normal approximation to the sampling distribution of x bar. So we start off with an example. So we have a population size 393, and XI is the number of patients discharged from hospital I during 1968. The mean, so we have 393 tickets. Each ticket is the number of patients discharged. So clearly this is not dichotomous anymore. Here we have a lot of different number tickets. The mean, we're told, is 814.6, and the standard deviation is 590. So a simple random sample of size 50 is taken, and our estimator for the unknown mu is x bar. So what we're asked to do is we're asked to find the probability that we're in the tail, namely less than 714.6 or greater than 914.6. So we can calculate the standard error using the formula that we were given last time, or that's in the review from last time, and we calculate that to be 77.95. So we can now convert our curve to a standard normal curve, and we see that the cutoffs here are 1.28 and minus 1.28, and so then the CDF of a number z is defined as the probability that your standard normal curve is less than z. So you can find this in R as p norm of z, and that's just what we need, right? So we can write our answer in terms of phi, and we find that it's 0.2. So then I asked you to do something similar with the dichotomous case. Here, this is the same hospital example, so capital N is 393 still. But now our tickets are going to be 0, 1, where we assign 1 if the number of patient discharges is greater than 1,000, 0 if less. And so we're told that P, the proportion of hospitals with fewer than 1,000 discharges, is 0.65. And I asked you to find this probability, and it's pretty much exactly the same type of calculation. So then we moved on to defining the confidence interval, in particular for our parameter mu, the population mean. But first, the confidence interval for a population parameter theta, it's a random interval calculated from the sample that contains theta with some specified probability given by the level of significance alpha. So alpha could be, for example, 0.05. Now, Z alpha is the number such that the area under the standard normal to the right of Z alpha is alpha. So I've drawn here a picture of that. And what it really is it's the 1 minus alpha times 100th percentile, which you can find in R using the qnorm command. So the area under the normal curve between minus Z alpha over 2 and Z alpha over 2 is 1 minus alpha, as is clear from this picture here. So we now move to the specific situation now where our parameter is mu, and we're going to write. So we're going to normalize x bar, our sampling distribution, which is so our sampling distribution is unbiased x bar. So we subtract off the center of the data, mu, and divide that by the standard error. And so the probability that that's between minus Z alpha over 2 and Z alpha over 2 is 1 minus alpha, as we just said above, and everything then will follow from that. We can multiply across by the standard error. That's the first equality here. And then the second equality follows just from the fact that Z bar minus mu is symmetric around 0. So if you just multiply this distribution by minus 1, it'll just reflect around the center 0, and because mu minus x bar or x bar minus mu is symmetric around 0, the area in the tails, or actually, I'm sorry, the area between the tails is the same. Right. So then it follows by adding x bar to both sides that the probability that mu lies between what's given here is 1 minus alpha, and that's called a 1 minus alpha 100% confidence interval for mu. Interpretation is that for, say, alpha is 0.05, there's a 95% chance that your random 95% CI contains mu. And in other words, 95 out of 100 times the 95% CI contains mu. So just remember from this form here, I'll just highlight it. So you can see that what's random here is the x bar. So this 95% CI is random. You'll get a different interval with every sample. What is fixed, however, is mu. And so it's not proper to say that there's a 95% chance that mu is in the confidence interval. You would rather want to modify the random interval. So it's there's 95% chance that the random interval contains mu. And so you can just look at an example here where if the true percentage of reds in a pail of marbles is 80%, then out of 100 95% CIs, these are the vertical bars here, out of 100 of them, 95% contain the true population parameter. In other words, crosses the vertical line, and 5 don't. Okay, so then I asked you guys to read this detailed proof here showing that the sample variance is an unbiased estimator of of the population variance. And this is really a line-by-line proof, and I don't really have anything to say about it. So I just like you guys to look at this and make sure it makes sense, and if not, come get some help. So then we started section 7.31, which is actually a step back. Here is where we prove that correction factor formula for the variance of the sampling distribution. So up at the very beginning, this formula. So this formula here we're going to show. In fact, we'll show both formulas. Okay, so that's what we're going to do now. And our treatment is going to be the one used in Pittman, which is, I think, a little bit nicer than the one in Rice. So I'm going to follow Pittman's derivation here. So we start with a population of capital N elements, and with mean mu and some known variance sigma squared. So for example, xi could be the annual income of the household in the US, and capital N is the number of US households. So capital X1 to capital Xn is some simple random sample. So x1 is the first number you pick out of x1 to xn, and x2 is the second number you might pick out of x1 to xn. So each of these have the same, so essentially the probability that x1 or x2 takes any value is equally likely. You're just picking a number out of a hat randomly. So in other words, these xi are uniform on x1 to xn. And I've written a summary of all the probability you should know coming into this class, and it's on B courses. And so this is page 3 of it, where, oh, lovely, here's the uniform distribution, and we can see that we have formulas for the expectation and standard deviation. So these formulas we're going to use right now. So I've just rewritten them here, and we're going to use that, so I won't say anything more about it. Let t be now a sum of x1 to xn. So the expectation of t is the sum of the expectations, just a property of expectations, and that's n times mu. So that means that x bar is mu as claimed. And now the variance of t, this we won't have time to finish, but we can see that the variance of t, because the xi's are not independent, that it's going to involve a sum of covariance terms. And the first thing we're going to do next time is see what these covariance terms are.